Gravitation is one of the most fundamental forces in nature, shaping the motion of planets, stars, and galaxies, and at the same time, dictating the success of every engineering endeavor in space. For engineers, especially those designing rockets, satellites, and space structures, understanding gravity is not just a matter of theory. It is a practical necessity. Every launch, every orbit, and every trajectory is ultimately a battle against Earth's gravitational pull. When a rocket leaves the surface of the Earth, it must overcome the immense gravitational attraction holding it down. This is why the concept of escape velocity, about 11.2 kilometers per second for Earth, becomes crucial. Engineers calculate payloads, fuel requirements, and thrust precisely with this figure in mind. A fraction less, and the vehicle falls back. A fraction more, and it risks moving off course. Gravitation therefore defines the boundary between Earth and space. Once in orbit, satellites depend on the delicate balance between gravitational pull and tangential velocity. This balance is what keeps communication satellites in geostationary orbits, weather satellites circling at polar orbits, and GPS satellites providing navigation from medium Earth orbits. For civil engineers venturing into space infrastructure projects, such as space stations or future lunar bases, these gravitational constraints are as real and important as the weight of materials here on Earth. Gravitation also introduces challenges like orbital decay, where satellites slowly spiral back to Earth due to atmospheric drag in low Earth orbit. Engineers must plan for station-keeping maneuvers, small rocket burns to correct orbits and extend mission life. Without understanding the physics of gravitational interactions, such corrections would be impossible. Beyond Earth, gravitation enables engineering marvels like interplanetary travel. Space agencies use gravity assist maneuvers, swinging spacecraft around planets to gain speed without expending extra fuel. This technique, a direct application of Newtonian mechanics, has allowed missions like Voyager and New Horizons to reach the outer solar system. Here, engineers are not fighting gravity. They are cleverly using it as a tool. The ultimate engineering challenge, however, lies in building structures and technologies that can operate under very different gravitational conditions. The weaker gravity of the Moon, the slightly lower pull of Mars, or even the near weightless conditions of deep space. These environments demand new materials, novel designs, and an expanded vision of what engineering means when gravity is no longer constant. In this way, gravitation is not just a topic of physics. It is the invisible architect of every space mission, every satellite network, and every vision of humanity's future beyond Earth. From the mathematics of orbital mechanics to the engineering of stable trajectories, gravity continues to test human ingenuity while offering pathways to new frontiers. This video is part of the series Physics for Engineers, Foundations that Build the Future, an initiative of the Physical Sciences Consultorium. If you found this exploration insightful, make sure to subscribe, explore more content from PSC, and join us as we uncover the deep connections between physics and engineering.